Good morning, everyone, and welcome to one of the external seminars for of ProperData. Today, it's our pleasure to have Emily Wenger, who is a new assistant professor at Duke University. And before that, she finished her PhD at the University of Chicago, and she spent some time as a research scientist in Meta AI. She has a great record that I'm not going to repeat here. You saw the bio. And she's going to talk to us about reclaiming data agency in the age of ubiquitous machine learning, which is very much of interest to this group. We're all thinking about data and the new challenges with all the generative models. So thanks for being here, Emily.
And thanks so much for having me. All right, let's get started. So I am a professor at Duke. I am excited to be here, and I think a lot about data and machine learning, so I'm glad to find some fellow compatriots in this conversation here. Let's move forward. So as you may have noticed, if you've been awake in the last 3 years, machine learning has suddenly turned up everywhere in the lives we live, from web browsers to mobile phones to financial services, healthcare, in our cars, and just in any interactions we have online. It's increasingly popular. It's a hot topic in so many industries, but regulations and controls for this technology are really nascent. As of now, we have the EU AI Act and GDPR, which are regulations in the European Union to try and put some guardrails around AI. And in the US, we really only have scattered biometric laws and some privacy laws in states like California and Illinois. Notably lacking are laws that guarantee transparency around model training data. Most existing legislation focuses on biometric use cases specifically and grander risks of foundation models. So there's really not anything that is regulating or providing any structure around model training data and consent and use around in that space. So given the lack of legal framework around training data and use of data, the reality is that these commercial models that are being used for profit in numerous settings are trained on personal data, and there's really no recourse that we have right now to prevent that. As this group is well aware, there are lots of problems that personal data use in machine learning systems can cause. The first obvious one is that user privacy can be violated through a variety of means, including models like generative language models, remembering and then regurgitating private information in training data. We can also have problems if users are enrolled in systems like face recognition that then compromise their privacy in real-life surveillance settings. There's also a second set of issues, though, that deal with user autonomy. When data is scraped or taken in some form, users can't choose how or when their data is used. It's just used. And there's also this economic issue that other entities are then profiting from the aggregation and use of user data through these machine learning models. Of course, people recognize that these are problems and there are a lot of solutions, but primarily, the focus has been on privacy and shielding data content from unauthorized viewers. This has taken many forms in the machine learning space, from encrypted model training to differential privacy to federated learning and lots of other great work. However, there are not a lot of solutions that address the second question of autonomy, because training or optimizing specifically for privacy assumes that data use is inevitable and that the best recourse we have is just shielding the content from prying eyes. But I think it's worth asking the question, is it? Do we have to assume that individual data will pass through these models, or can we design mechanisms that give people more choice over that particular question? To that end, I argue for an alternative solution called data agency, which has been a lot of my work in my PhD and dissertation and now at Duke. And I define data agency as an individual's ability to know and control how or if their data is used in machine learning systems. I view data agency and mechanisms around it as alternative and complementary to existing privacy solutions. I believe they can and should work together, but agency takes a step beyond and tries to give levers to people to decide when their data is to be used. There's a lot of mechanisms that we could use to enforce data agency, legislation, corporate policies, and technical tools. Legislation is a very reasonable course, but it's slow and sometimes very, very difficult to get past depending on political climate. Corporate policy would be nice, but somewhat requires a fundamental shift in how companies view user choice. And then technical tools, which will be the focus of today's talk. I believe technical tools can provide foundational components of data agency that could promote and enable reasonable corporate policies and legislation around this topic. So in today's talk, we'll look at why data agency is even possible in the machine learning setting. Then we'll discuss some data agency solutions that my work has set forth, and then we'll have some forward-thinking discussion and time for questions at the end. And I'm not sure the protocol in this seminar, but if there's clarifications or questions that anyone has along the way, please stop me and I'm happy to answer them. The key intuition behind the reasonableness of data agency is that machine learning models learn from data. So in this sense, users have some power in this equation. The data we provide to these models ends up affecting model behavior, and we could leverage that relationship between data and models to affect some change. This is a very simplified view of how data passes into machine learning models, where groups of individuals generate data that's then collected from various sources and used to train a model. And I believe data agency solutions can leverage this influence that we see in the directionality of this graph to disrupt, detect, or deter unwanted data use. And I view each of these solution types as acting at different points in the training pipeline. And there are obviously more ways that could be explored here, but these are the three mechanisms that I'll focus on in today's talk. As I alluded to, the proposed data agency solutions operate at these different points in the pipeline. Disruption solutions will make individual data unusable and therefore give control of data use back to the individuals. Detection solutions trace whether or not individual data has been used in a model to serve as evidence in a court case or other situations where knowledge of data use is more important than prevention of data use. And then finally, I'll explore some new work that I have on deterrence of data use by monitoring and preventing data scraping, and that's through a data scraping microscope that I am building here at Duke. We'll start by talking about disruption solutions. Disruption is designed to make individual data points unusable. And one of the first forays into this space that I worked on was a tool called Fox, and it was meant to prevent unwanted face recognition. It did this by changing how user images are perceived by machine learning models and essentially exploiting a gap between human and machine learning perception of content to prevent this unwanted recognition. At a 50,000 foot level, this is how Fox works. We have here on the left a basically two-dimensional representation of how a facial recognition classification model would view images of people. You can see the different ovals. Those represent different people that the model has learned to classify, like Emily, Beyonce, Heather, Ben. And then the icons within the ovals are actual images seen during training. And you can see that because the icons map well to the actual feature space of the person, if this model encounters this selfie of me, then it will map that selfie to the correct part of feature space and I will be classified correctly. However, if this model is trained on cloaked images, in this case, cloaking is an optimization procedure that pushes my images towards the feature representation of others. So in this case, I've been cloaked to look like Beyonce. And so the model trained on my cloaked images has learned this complicated decision boundary between me and Beyonce, but knows nothing about my true feature space down in the bottom right. That means that a model trained on cloaked images will see this selfie of me, see it appear in what it views as a large feature space all belonging to Ben and be unable to classify me correctly. Fox kind of took on a life of its own after we published it. There was a significant amount of downloads, several 100,000 people adopted it, and we started, relevant to the next portion of this talk, a listserv where people would email us questions, concerns, bug reports about Fox. And it was a very interesting learning experience to interact with the community that used our tool and to understand better their needs. But after a couple of years, we got this really interesting message in our listserv from someone named Kim. And Kim asked if the tool like Fox could be used in a different setting in preventing the use of AI to learn from paintings and illustrations. And we thought it was an interesting question. So we started digging around, talking to people. Was that a question?
Yeah. Can I ask a clarification question?
Yeah, of course.
Slide. Hey, this is Kostas.
Hi.
Hi. Great topic. So when you essentially overlap the feature space of multiple people or a couple of people,
yep.
Is the idea of the optimization to actually maintain, as far as the human brain is concerned, a very similar image?
Yes. Yeah. So it's a dual objective optimization that minimizes pixel space disruption while maximizing feature space disruption.
Okay. Sounds great.
Yep. There's a question in the chat. I can't really read the chat. So
Zubair, you want to tell your question?
Yes. In your previous slide at the threat model where you were like systematizing all the different work you were doing.
Yep.
I was yes, right here. So you're talking about data, but it was a little unclear to me when you say individual data. What does that mean? Can you draw a distinction between public data, for example, stuff I write on Reddit, versus private data? For example, my pictures that I'm sharing with my friends on Snapchat.
It's a great question. Generally, when I refer to data in this talk, I'm talking about content that you create that gets shared online in some way. So private communications would not be classified as the data that I'm talking about here, but I think there could be interesting solutions and discussions around that type of data. Does that clarify?
So you are dealing with public data?
Public data, yes.
Okay, got it. Thank you.
Yep. Okay. So we got Kim's email, led to some interesting investigation. And what we realized in our reflection and conversations is that, yes, using face images for AI training can cause downstream privacy issues. And that's a problem. So Fox was addressing a real issue. But the use of art to train generative AI models actually has a significant impact on artists' livelihoods. And we kind of came to understand this issue better through conversations with a lot of artists, including people like Kelly. Kelly is an artist, and she has always been one. She has this style that in her early years wasn't really present, but as she gained skill and confidence, she developed this very unique, beautiful style of artwork. And it's made her a very successful professional artist. Now Kelly has a business where she posts her art online on a personal website, on portfolio websites like ArtStation, and on a personal Instagram, and then uses the publication of her work to make commissions and online sales, including things for musicians like Evanescence. That's been a really profitable business model for Kelly, and she makes a decent living for her family, until she found out that her paintings have been scraped from these online repositories where she shared them to publicize her product and used to train image generation models. She didn't know, she didn't get compensated, and she didn't certainly get any credit for the contribution she made to the model's performance. And when you then look at the art that a model trained on Kelly's images can create, you can see it's pretty good. If you give it a prompt, make this woman in the style of Kelly McKernan, on the left is what the AI did, and on the right is what Kelly did. So it's essentially imitating her style to a level where someone might not consider paying Kelly to get a print of this work because they can just make an AI version. And what happened to Kelly is not unusual. Style mimicry is an industry. We see lots of different style marketplaces popping up where people will train generative models on particular artists' portfolios and then offer them as available for free download to anyone who wants them. Although ironically, asking for donations for their part in training the model, but not compensating the artists themselves who provided the training data. So essentially what's happening in the art community is this, which is tough. There's a lot of harm that's coming to artists' livelihood based on a user study that we performed in January 2023. And obviously, we cannot solve this problem. This is a huge economic issue, a shift in how our society is functioning as generative AI becomes more popular. But we wanted to do something that pushed back, something that changed the narrative and gave the possibility of a different relationship between data and models. And what we ended up producing was a tool called Glaze that was designed to protect artists from unwanted style mimicry by AI models. This is the fun Glaze headline of, if you glaze your art, it disrupts the underlying style envisioned by the model, again, exploiting this disconnect between human perception and model perception and preventing effective style mimicry the way that we were seeing with Kelly's art before. You can read the paper for a lot of details, but I will just give you some of the highlights here. Essentially, as I shared, without protection of their portfolio, an artist's images can be used to train a diffusion model that can mimic their style, and then someone could take this model and just freely generate images with different prompts that mimic different portraits or paintings in this artist's style. Glaze then adds an imperceptible, as with Vox, layer to this art that disrupts the artistic style features that are most relevant to the artist's presentation of the work. And then a downstream model trained on this kind of disrupted art will be unable to mimic the artist's style. The visual disconnect between original and glazed work is very subtle, and we worked a lot with our partner artists, including Carla and Sarah and others, to make sure that the algorithm performed well across different types of artwork, like portraiture and cartoons and photographs. So the artists seem quite satisfied with the level of disruption that it provided and believed it did not disrupt their ability to share this art freely. So here is just a broader visualization across different styles. Was that a question? Nope. Okay. A broader visualization across different styles of how Glaze performs. So the different rows represent different artists. Nathan Fox at the top is a concept artist, and then Monet and Van Gogh are Monet and Van Gogh. Without protection, style mimicry can achieve results like this, which is quite impressive and difficult to distinguish from the real artist. But with protection, we've distorted the underlying understanding of style and prevented art from being mimicked in this way. In the original Glaze paper, we explored robustness to a variety of countermeasures, including different adaptive attacks that an attacker could employ to get around Glaze, even with knowledge of the algorithm, and found that for all those things we tested, it was highly effective it was not disrupted by them. So we moved ahead then with considering the question of widespread deployment.
Can I ask something?
Yep.
Hey, so can you tell us, unless you plan to talk about this anyway in the future slides, like the main idea about how you do this? Because I'm aware of different ways of doing this. You could add noise, you could look at the features, you could try to optimize and figure out where to add noise, what kind of noise, how to move features. Is this kind of like inspired by the algorithm you used at the previous work? Were you basically, okay.
Oh, you're asking about like how the Glaze optimization works?
Exactly. So what is
yeah, unfortunately, I cut that slide for time. So I can give you just a high level overview here. I'm really taking you at a 30,000 foot view of all these things. Essentially, what we use here is, again, a dual optimization objective where we're minimizing visual distortion via what's called LPIPs, which is one of many mechanisms you can use to keep images, to measure image similarity in an optimization setting. Then the feature space that we're looking at changing, we define using what's called a style transfer network. They're generally designed to take in an image and then recreate that image in a different style. So, it's a picture of me, but then the style transfer network turns it into cubism. So it has that nice property of moving art between styles in the way that we would want to prevent mimicry. And so we do the dual optimization using LPIPs on the visual side and then the style transfer network on the feature side, and then just optimize to move the particular piece or pieces we want to protect into a style genre that's very different from the original while minimizing visual distortion.
Okay, sounds good.
Yep. So when we went to deploy Glaze, we obviously considered risks. We did a lot of adversarial analysis of Glaze, but as is the case in the field we call adversarial machine learning, it's very difficult to prove security, if not impossible. So we knew that there could be future attacks. And we also were worried about being misunderstood by artists as a silver bullet that we were not. We were a tool that would probably work well, but could not be predicted to be future-proof. But in the end, the artists that we worked with convinced us that they would benefit from this tool and that it would be of great use to their community. So we went ahead with deployment. And since deployment, there have been millions of app downloads. Hundreds of thousands of artists appear to be using this tool. And we've gotten so much wonderful and supportive feedback from the art community, which has been really wonderful. They felt very seen and protected by this tool. And we were glad to provide them some measure of hope as generative AI becomes an increasingly disruptive force in their world.
Okay. Zubey, you have a question?
Mm-hmm.
There's a question.
Yep. Go ahead.
Yeah. Related to the previous slide, given that Glaze is not feature-proof, so in the long-term robustness is not guaranteed.
Yep.
What exactly is the utility of it? I ask because in our an NSF project where we look at online tracking, it seems to me like this is essentially similar to do not track, which is a signal your browser or device can send that, hey, do not track me, but there is no regulation, there is no guarantee that it will be respected or it will be applied by.
Yeah. I'm kind of going to talk about this right now in this slide. Can I defer your question to after this? And if it remains, you can ask again.
Yes, thank you.
Cool. So as somewhat expected, we have seen work demonstrating computationally expensive but effective ways to evade Fox and Glaze. Essentially, these works optimize away the perturbation using a variety of techniques and demonstrate some level of mimicry success. Ultimately, mimicry success is in the eye of the beholder, so you can decide for yourself whether these mechanisms, evasion mechanisms, are totally effective or not. But for the purposes of this conversation, they're somewhat effective. But the authors of these papers also argue that the publication of works like Fox and Glaze provide a false illusion of security and is irresponsible research, which was a bit of a harsh criticism to receive as a young researcher. And so it's prompted a lot of soul searching, at least by me and by other members of our team, as to whether this was the right thing or not. To the question posed before, there's an active team working on patching issues that we find with Glaze, evaluating against new models, ensuring that, to the best of our knowledge, the mechanism of protection is still effective. But as these works show, there's always something we could miss, and that's the burden on the defender in any security scenario. So I'm still thinking about all of this, but here are a few thoughts that I've had in the course of my thinking. The first is that it's kind of a lose-lose situation. If we don't provide artists with some sort of temporary relief from the scraping, then their livelihoods are harmed. So giving them Glaze gives essentially model trainers a bit of a pushback in saying, hey, people might be doing things to their data that's going to harm your model, so maybe consider not scraping their portfolio. But as these pushback works showed, anything we do is somewhat impermanent. So that's difficult. I also think legislation alone won't solve this problem. In conversations with policymakers, they believe that technical tools will solve all these issues with Not all of them, but some of them say that technical tools will solve the issues we're seeing with copyrighted data use in AI models. And it seems like many technical people think legislation will solve it. So I think there has to be a balance of tools like Glaze and Fox that provide some technical grounds of pushback, along with legislation that puts guardrails around data to protect people's intellectual property. And ultimately, I think it's right that the research community should encourage creative solutions to this problem, while being clear-eyed about their limitations. It's an ongoing conversation. Nobody knows what the right solution is, and Fox and Glaze are one potential way to go about this. So I'm not sure if that answered the question, but this is kind of my thinking on the problem right now and my response to some of the robustness questions.
All right, Jeremy has a question.
Yep.
More a comment. I'd argue that what you're saying is pretty much the same as what we've been saying in the cybersecurity field for decades, that we know at some level how to build completely secure systems, but it's not cost effective to do it. So we do things that we can, and we get some of it, even though we know it's not perfect, because the alternative of doing nothing is far worse.
Yeah. Yeah, the cat and mouse game is real, but it seems like it should exist because, like you said, doing nothing is far worse. Unless there are any questions. Oh, go ahead. Sorry.
Sorry, a quick question. So I wonder if there is, in cryptography, we have sort of the concept of forward secrecy, like basically, giving some guarantee that system is secure until it's not, but retroactively, if an adversary, for instance, in case of confidentiality, an adversary has recorded encrypted conversations, cannot, even if they break the system and they get a hold of the key, let's say, they cannot recover past conversation. Do you think it would be possible to have something along these lines with this kind of work where you can at least sort of protect past perturbations, past defenses, and then once a new technique to break this kind of this kind of defenses are deployed, then okay, you stop using it, but what you have published before is still safe. Is that something that could be feasible?
I don't know. I think the difficult thing about securing machine learning models and securing things in the context of machine learning models is that it's very difficult to prove anything, make any proof if your model isn't a linear regressor. Once you get into the complexity of, transformers or neural networks, you can't prove anything about their security because it's too complicated. And it seems like the suggestion you have of forward security would require some level of, mathematical proof for some hard problem. And I don't know what that would be. Maybe I'm not creative enough to think of it, but it seems like a very difficult thing to do. So it seems that the best defense in these sorts of situations is an economic one where you just make it expensive enough for someone to break something rather than trying to prove it totally secure in some way.
Thanks.
Any other questions? Otherwise, I'm going to shift gears a bit. Great. Zooming back out to our vision of how data agency solutions could work, the next category of things that I've thought about is detection. The context for solutions like this is you want to know if a specific machine learning model was trained on your data. And there are a lot of, and in fact, a growing number of real-world examples where this kind of query would be important. One would be to check for compliance with the EU GDPR Act and their right to be forgotten, which says that if you want, you can be removed from a model, or your training data can be removed from a model. And there will probably be other legislation, particularly as these court cases about AI and content copyright are settled, that may arise in other countries and settings. So the solution we came up with for this problem was creating essentially modified data points whose influence on the model during training can be easily detected by model queries. So these data leave a statistical signal in the trained classifier that we can then back out and infer with high probability, even with only black box access to that model. The motivating scenario and threat model here is you have someone like Alice who shares some images online. So again, we're considering really public data here. And after some time, they see that maybe a platform that they shared images on has offered a new model. And Alice is curious if their data was used in some way to modify or train, or excuse me, was used to train that model. And they don't really have any recourse in the base case to know that. But if they were to use our data isotopes method in the process of sharing their data online, perhaps they could answer that question. The difficulty in this situation is that as one of many individuals contributing data to a large-scale data set that's then used for model training, Alice has essentially very little control over what their data, how their data is used. So this table here is on the rows, we have kind of the flow of data from Alice to the platform where it's hosted, to the model collector, to the model trainer. And on the columns, we have different types of content. So data content, the data labels. So is Alice's data labeled as a dog or a tree or whatnot? And then the model training itself. So we can say that with some confidence, the model trainer on the far right column has control over everything. They totally control how model training progresses, and they can totally change all the labels in the data set that they have. However, we assume that both the person who collects the data and the model trainer don't mess around too much with the data content in their data set because they want it. That's why they got it. They think it's valuable. And that's the kind of in we have to give Alice some power in this situation. We'll assume for the sake of argument that the platform doesn't do that much to the data it hosts, besides maybe compressing and uncompressing it. But Alice only really then can control the content of her data. And so somehow we have to create a solution that can detect downstream data use by only manipulating the content of the data Alice originally shares. There's a lot of assumptions that we are working with here, again, to make this as realistic as possible. So we assume that Alice doesn't know what other people contribute to the data set. And there is prior work that does assume that, but that's not relevant for the case we consider. We can't, again, change the labels of the data. And so Alice couldn't use something like a backdoor to check for data use. She doesn't know what kind of model is being used downstream, although we do make the assumption that is a classifier. Extensions to this work should consider other model settings. And then we finally assume Alice has query-only access to the model. White box access is hard to come by, and black box access is much more common. So the TLDR of all this is that existing solutions made assumptions that were not compatible with real-world scenarios like the one we consider, and so we designed our own. The ultimate proposal is something called data isotopes. So Alice marks her images with a spurious feature. That's a feature not characteristic of her class, and that creates a data isotope. So for a toy example here, Alice could mark her data with this little turtle that's gently blended into the background of her image, of some subset of the images that she shares. And then if that image, the marked images are used during training, this spurious feature is learned as associated with her class in the model. And then she can use the spurious feature in a testing procedure to detect the use of her personal data. This mechanism works because the isotope changes the distribution of probabilities in the model's output predictions. Essentially, training on the isotope marked images increases the probability of Alice's label for images with Alice's mark. It doesn't necessarily elevate it to the highest probability in the softmax distribution, but it does increase it enough to give a signal. So just as kind of an example here, this model was trained on isotopes images for class 7. So Alice's class is 7 in this model, and the other classes don't have the isotope mark. So when we present this model with this woman's picture, we see in the label index, and this is kind of a visualization of the softmax probability that comes out of the model, that the probability of Alice's class, the mark class 7, is very low. But then we query again with the turtle blended into this image, and we see this increase in the probability of Alice's class. It's, again, subtle, but it's enough that if you repeat this with multiple images from multiple classes, you can have some guarantee that you actually have a model trained on images with this particular mark. Again, sparing you a lot of details, but we test this in a variety of scenarios, and we find that this mechanism performs well in large models up to ImageNet scale. In machine learning as a service, where there's very little information available about how the model is trained, we wanted to make sure we weren't biasing ourselves in how we were training the model to make isotopes work, and that's fine. And this is detection true positive rate. And for some reason, I represented one as a percent and the others as proportions, so my bad. And then in transfer learning, so even when the full model is taken and then fine-tuned for a new task, we see that in that new task setting, the isotope signal will persist, which is exactly what we want. We also looked at countermeasures. Again, like Fox and Glaze, there's no guarantee that we can really provide here in terms of efficacy, but we can test the array of countermeasures that are reasonable for the model trainer to try. And we find that all fail, or using the economic argument, impose a significant cost on the trainer that they would be unlikely to want to incur. There's a lot more details about that in our paper. I think there's a lot of interesting work to be done here, exploring other domains, proposing theoretical explanations. I think the value of this kind of project is that it takes what is traditionally viewed as an attack in machine learning, which is membership inference. We talk about membership inference as a privacy risk if we infer an element of the training data set. And I think in this case, membership inference is an asset, because if your data is used without consent, then you want to be able to infer that your data was used. And so I think there are probably other things that we currently think of as vulnerabilities in machine learning, like this membership inference case, that could be exploited as privacy preserving or agency preserving mechanisms. And so I think that would be another avenue of exploration here. And then I'm working on a project that's pretty young, trying to see if we can make these isotopes tamper evident, because my lawyer friends tell me that you couldn't use something like this in a courtroom unless you had some proof of non-modifiability or the ability to detect that something had been tampered with. And so we're exploring whether it's possible to extend this to that scenario, and we'll see what happens. Any questions?
Costas has a question.
Yeah.
Hi.
So this is great, also quite interesting. So if, I would like to ask your thoughts about the following. I like the economic argument in all this type of work. So looking at what you have done on the second case and the temper evidence stuff you just discussed, there is a trade-off here, because if you assume that you actually have some knowledge of the distribution of the data, you can do your isotopes or watermarking in a better way, meaning in a way that will allow you to be more temper evident. It takes a difference when you design it, when you do your optimization, you will be able to get under certain assumptions guarantees, if you wish, even probabilistic guarantees, but only if you know something about the general data. You see why, right? Because you want to distinguish what the model learns for the particular data you have.
Yeah.
So you need to know the distance of that data as compared to the rest of the data that the model has been trained over. So in some sense, the more work you put to collect this data, right, and learn the distribution, the harder you make it for the other guys, speaking again of the cat and mouse problem, right?
Yes.
To kind of figure it out that you didn't take it out. And at the same time, the more work you put, the less you distort your own image to achieve the same, right? So there is a trade-off here with respect to how much work you put in advance versus how much work you force the other guys to put. Versus how much you distort your image to achieve your goal. I'm wondering whether you have looked at this trade-off at all.
No, I haven't. It's a very relevant point, because I have a student who's just starting to work with me, and she's in computer science and economics, a graduate program on computer science and economics. So that would be a very interesting program to explore with that kind of setting. So no, haven't. Very interesting idea. Happy to chat more.
Sure.
Yeah.
I'll be glad to.
Yeah. Great. Thank you.
Emiliano, you want to go next?
Yeah, sorry. I sort of missed I think the previous slide. You were talking about membership inference attack. So my neighbors are doing some work, and it was really loud, and I tried to kind of move. But so could you please sort of clarify what you were saying there? I apologize for missing that.
No, you're good.
Yeah.
There wasn't a slide, so that's part of the
Oh,
problem.
okay.
I'm sorry. But essentially, I was saying that this isotopes thing takes what's traditionally viewed as an attack on a machine learning model, which is membership inference, inferring whether something was an element of a training data set, and turns it into a tool for user agency. And that's not I think that's a reasonable flip of the general consensus around what membership inference is, because so often this data is taken without consent, that knowing if you're in it is valuable rather than a privacy issue. And I was connecting that to a broader point of, maybe there are other things in this space that we traditionally view as attacks that could actually be reframed to be user-friendly defenses when you rethink about who's an adversary and what they're doing.
Right. So basically, you could sort of use a membership inference attack to sort of argue that your data was used to train a model? Or?
Yes, exactly.
Okay. Right.
Yeah.
So we actually sort of advocated that a while ago when I was in the UK before moving back to California, and there was a case there where Google DeepMind had used healthcare data from the NHS, the National Health Service, allegedly for purposes other than what they had given access for.
Oh, I remember
so
this
to train a model, right? So we had advocated using that, and we got a lot of pushback because you kind of have to prove something that holds under a null hypothesis. And I think there was actually a paper being published at least on Archive from maybe ETH and Waterloo, like arguing that it's very hard to do actually to do that. So I just wanted to share in case that's useful to you, maybe like about this paper, about this pushback, and be happy to chat a little bit more if you're just.
Yeah, that'd be great. I know there's a new paper from Mike Reiter, who's also at Duke, that was at CCS this year, that basically took what we did here and then bounded the false positive rate on it, which is not quite the same as what you're talking about, but it's at least some guarantee. So yeah, but would be happy to chat more.
Yeah, let me see if I can find the paper while we're still online.
Thank you.
Thank you.
All right, I'll just move now into the final section of the talk. I'm leaving lots of time for questions at the end, so I have about 5 more minutes of content, and then we can chat. The last thing, and this is very new work since I've been at Duke, but the issue that I noticed, or a common thread that I noticed with all my prior work that's been presented here, is that you don't control your data hosting. And so all of the stuff that we talked about, isotopes and Glaze and Fox, assumes that puts the burden on the individual to modify their content in some way before it's shared, whether to detect its use or to prevent its use. But there's this middleman that also is operating called the data host, whether it's a website or a social media platform. And data scraping certainly harms the individuals whose data is taken, but it also harms the data host in that they may experience increased traffic and network latency, and also perhaps they have some vested interest in preserving the data on their particular sites and preventing it from being scraped. And so I'm kind of curious about moving up the chain of data and seeing what can be done at this next level of protection. And so I have this nascent collaboration with the Duke's web team to use the weblogs from Duke University as a microscope to understand AI data scraping at scale, and then hopefully develop some countermeasures. There's so much discussion about forming AI data sets from scraped data, but there's really no research or very limited research around what's happening there and what can be done. So again, very new. I've been at Duke 4 months, but we have some initial findings. We have, millions of anonymized web records over time. And basically we find that robots.txt is not respected. Robots.txt is the one thing we kind of have. It's not codified, but it exists to prevent bots from taking data that they're not supposed to. But it seems that they're not really respected. And in conversations I've had with scraping companies, they just admit this. They say that robots.txt is anti-capitalist or something, and so therefore they shouldn't have to respect it. But other companies like the New York Times view robots.txt as something that should be respected and useful, and so they have some issue with that. And it's been interesting to observe some conversations between people like that. We've also found a lot of spoofing around user agent bots. And so that's something we're investigating further to understand, if we don't even know who the bots are that we're working with, how can we develop mechanisms to prevent them from scraping or taking data they're not supposed to? And we've also found that these AI scrapers or bots that we believe to be associated with AI scraping can account at times for up to 50% of all Duke web traffic, which is kind of crazy because that has led to some website takedown on the Duke end, not from any malicious activity, but just because these scrapers are going crazy. So we have lots of things we want to do with this project, including honeypots to detect or to track data propagation through models, and eventually, hopefully, some mechanisms that can kind of automatically move scrapers through lower priority network paths to maybe find a common ground between still sharing data that might be useful while not compromising the integrity of the host. So lots more work to do here, but it's been certainly an interesting foray into something very different. Any questions about that? I saw something in the chat, but maybe that's the paper. Okay, so I'll just wrap up with a few thoughts. To pull back this image from the beginning, we really are living in the Wild West of machine learning. It's fun. I think it's been very interesting to watch things unfold from the technical and legislative side, as well as I've alluded to, court cases. And I think in 5 or 10 years, many of these issues will have some better resolution, but it's really fun to be part of building better, safer machine learning systems that respect people's data rights. I think, as I've alluded to, data agency requires both tools enabling knowledge of data use, like isotopes and things much better and more robust than isotopes, and mechanisms to control data use, whether it's Glaser-Fox or other technical tools or legal tools or some combination of all of them. And there are so many other things I think could be done in this space. So obviously, more collaboration between government and academia to build tools that can actually enforce regulatory standards and standards that can actually be enforced by regulatory tools. I think machine unlearning and its relationship to the right to be forgotten is an example of this not working out because machine unlearning is really hard and the right to be forgotten is very difficult to actually enforce technically. Revisiting data agency through the lens of model collapse, I think would be very interesting. There's been new work showing that if you train generative models on their own content, they just spiral into badness. And I think there's some interesting questions to be explored here about, controlling models based on the threat of collapse and what data can be done, what we could do with our data in light of that known consequence. And then in reference to my last point, tools to prevent unwanted scraping would really, solve a lot of these issues at the base, because if the issue is that data is being taken without consent, if we can just stop the taking of that data, that would be great. And then just a final note, I do other things too. And so since this is a broad group of researchers, I just wanted to highlight that I study AI security and society. And so on the security side, which this didn't really touch on, I look at kind of issues that arise when we put AI models in the real world, as well as this kind of project on using AI models for cryptanalysis. And then I also look at issues of AI on society, which include data agency, model collapse. I'm looking at homogeneity issues in large language models and some user studies around that. So if any of these topics are of interest to you or you ever are interested in chatting more, please email me because I'd love to build some collaborations. And now I'll just leave the last couple of minutes for questions.